percent deviation from ideal behavior, it's the absolute value of P real minus P ideal. Oops. Divided by P ideal times 100. Let's go ahead and just wall this off. So what goes in for our P real? We get 3.0854. Minus P ideal, which is our 3.89. Times 100, and we should get a value of about 21%. Does it sound like a lot? It kind of is a lot. So think, is 95 Kelvin, is that cold or is that high temps? 95 Kelvin, cold or hot? Well, room temperature is 298 Kelvin, so 95 Kelvin, that's cold, right? So at cold temperatures, as well as high pressure, I mean, one mole of gas is kind of high pressure, but definitely the low temp is causing this really significant deviation from ideal behavior. What do you think the percent deviation would be under the same conditions for, say, xenon? Do you think the percent deviation would be higher or lower? What has a higher correction factor? CO2 is 3.59, xenon is 4.19. Yeah, so xenon, if you look at the correction factors, xenon has larger correction factors. So what do you think the percent deviation would be for xenon? Higher or lower relative to CO2? Be a higher deviation, right? So carbon dioxide, molar mass of 44.01 gram per mole for CO2. Xenon's 131 gram per mole, right? So higher molar mass means greater dispersion forces, meaning greater sticking of molecules, which means more deviation from ideal behavior. And you'll see that in the calculation here. So it's kind of like, you know, how do they know that dispersion forces happen, right? How do they know that, you know, dipole-dipole forces happen? Like, one way to investigate the physical properties of matter is to look at these deviations between ideal and real pressures. Right, you know, and so that's one, you know, observations like this and laws from gases like this and calculations have led scientists to the conclusions they have. So, you know, it's sort of like, you know, yeah, well, dispersion forces happen because the teacher says it happens. Versus, well, no, the teacher says it happens because this is the scientific evidence that supports that, right, you know. So, so I'm kind of, you know, showing you this to really, you know, from a scientist perspective, this is how we know these things happen, right? Any questions about VanderWaals equation and real gases? Keeping it real, as they say. Any questions on the units? So just to real quickly summarize, we solved the VanderWaals equation for P real. We then plugged in the numbers using the correction factors for carbon dioxide gas, paid attention to our units and sig figs, And then we did the same thing for the ideal gas law, which is a lot easier to calculate, clearly. And we just took the difference between the ideal and the real pressure, absolute value of that, right? And then divided by P ideal. We always divide by P ideal because it's percent deviation from that. So that's why we have P ideal in the bottom. Right? It's just like percent relative error, like in our error analysis, right? It's always relative to the trusted value or the accepted value. All right, so the ideal value is kind of like that in this case. It's not accepted, but it's relative to that. Okay. All right. Is your brain sufficiently cooked? Okay. Let's take a little break and go upstairs. Meet you up there.